Excellent. I'm just going to put on.
Okay, well, good afternoon and welcome everybody to our virtual Lunch and Learn. We've been at this for a few weeks now, and it's been overwhelming the amount of interest we've had in the Lunch and Learns, and really as a way to connect with people and keep our industry going at a time of when a lot of us are locked down or shut down, or as I like to say, staying safe at home. It's been great that all of you could join us. So I'm Richard Rastuccia, Vice President of Water Management Solutions for Jane Irrigation. And I'm really happy to say we've got a great presenter again today, and that is Perry Continente. And you certainly get a feel for these lunch and learns when you send out your invitations. And I was telling Perry, we sent out his invitation on Monday, and I think within 30 minutes we had 50 people signed up, and that's pretty popular. And I think one of the main reasons why that is popular is people know Perry from his training with the IA. I think they know him as somebody who not only knows the intellectual side of irrigation, but also uses it practically in growing and helping growers. And so as a result, he's got a really big following. He's also got a degree from Cal Poly and a fantastic reputation in the industry. So again, I'm really happy to have Perry here today. And with that, I'm going to turn it over to Perry. Perry, good afternoon.
Good afternoon. Good afternoon, everyone. And thank you, Richard. That was very kind. Anyway, today we're gonna discuss 10 design considerations for efficient drip system, and so we'll get going here. So it does seem a little bit, I haven't done too much of this remotely, but here we go.
Yeah, and Perry, I just want to make mention that you're going to have some questions for Perry during this chat, and with as many people as we get on these, it's preferable that you type your questions into the group chat, and I'll feed those into Perry either during or after the presentation. So.
Okay, yeah, because I believe the questions will help, because we're not going to get too deep into any one subject because of the time limitations, of course. So anyway, the first and most important is to give the grower what they want. I have to tell you that I've made that mistake before. So even though you may give you may present something to someone that might be a better, you might consider it to be better. If it's not what they want, you're going to have a problem. So anyway, that's a good thing to learn early on in your career. So anyway, the goal is to provide an application that will meet the peak ET, or essentially the water crop requirement. And so the tools we have to give to the grower are what's your distribution uniformity and what's your application rate. And once they know those two things, they can intelligently irrigate their field. Anyway, so we're going to provide them with a high DU or an appropriate DU. I won't get too far into that, other than to say that as a general rule, we target 0.9 or higher. And most people consider this to be like, think of it as a percentage, but in the world of Irrigation Association, we refer to it as a decimal. Okay, so anyway, I think another thing that's often not addressed is to provide a fertigation chemigation strategy, or understand what their strategy is so that they can apply it or have the tools to apply it through their system. Okay, so one of the first things we're going to do is we're going to talk about a few definitions, because people tend to talk and use terms, and if we don't all understand what those terms mean, then we're kind of talking past each other. The two most important terms, or things that we need to understand, are emission uniformity and distribution uniformity. The takeaway here is with distribution uniformity. Essentially, it's just what it sounds like. How evenly are we applying the water over our field? And we look at irrigation efficiency, it's probably not a term that we should be using, because if you look at the equation, If you under-irrigate your field, you'll have 100% irrigation efficiency, and it's really not what we want. Application efficiency is used generally to describe or the performance of a single irrigation event. So the takeaway here, by the way, emission uniformity, distribution uniformity are really the exact same thing. Only we tend to use the word emission uniformity when we talk about, like, say, a single lateral. And we say, okay, the emission uniformity of my single lateral might be 0.92. And the distribution of uniformity of my submain, or the pressure variation in that submain, is going to contribute to loss in DU. So the emission uniformity of my submain versus the emission uniformity of my single lateral gives me a global DU. So that's why, so essentially the definition is exactly the same. So for those out there who think that there's a difference, there isn't, okay? And I'll say one thing, that you can go right now, you can go onto the Jane website, and you can use their length of run calculator, and it'll tell you what a single lateral emission uniformity will be, or and so you can arrive at your distribution uniformity of your system if you take that into account. So you can use it as a design tool, actually. Okay. So how to make sense of the design. So now this is like a typical design. This one was done by IDC. You can see that there's elevation, and there's a whole list of things that we need to understand. So this allows the installers to install it, and it also tells the irrigation, the customer, essentially what he's getting. Okay. So what do we gain from this, or what are we looking at? Essentially, we can understand, what the site looks like. The topography is really important, of course, to the designers, and we also, the other most important thing is the soil type, or understanding the soil texture, and this gives us an idea of how much we can expect the soil to hold in water holding capacity, and also wetted area, and those are two very, very key things when it comes to irrigation design. Okay.
So Perry,
excuse me.
I just want to ask a question. Initially, I really liked what you said about listening to your customer, right? Delivering what your customer wants. And I'm sure that you've seen customers, and the scale of their knowledge and what they want is all over the board, right? But so how do you hone into that? How do you learn that about your customers?
Well, let me just give you the example of why I said that. I once did a very, very small drip system for a customer who wanted sprinklers, and he wanted sprinklers that were like impact sprinklers. He wanted to wet the whole area, and I sold him micro sprinklers. Now the system was perfectly good. It watered the trees beautifully. The trees showed no stress. It was great, but he hated it. And the reason he hated it was just because he couldn't see the water going all over. So essentially I had to change it back. I changed it back to what he wanted. Now, what he wanted wasn't necessarily bad. I mean, if it were really bad, I guess I would have tried harder to talk him out of it, but it was just different.
Yeah.
And so that was a lesson I learned early on.
Yeah.
Well, so that's now if somebody wants to do something that's inappropriate, and I won't do it. Either I won't do it. I can either walk away from it, or do an effective job of convincing them why it's not a good idea. And I have a slide later on that's going to I'm going to show you an inappropriate emission device, and it's obvious.
Yeah, so there's some deal busters, but there are some times that it is, yeah. I mean, many times it's important to listen to your customers. So that's a great story. Thank you.
Yeah, so you do need to give people what they want. Yeah. and a lot of times, people tend to gravitate towards appropriate technologies. And, so you can look around and you can see that everybody else in the neighborhood is doing something. You know, look at your neighbors, look at what your neighbor's doing, and take that into account. You know, so there is a good reason to do that. Anyway.
Yeah, great. Thank you.
Okay. So now system flow rate requirements. This is probably one of the most important things we're going to do as designer, is to make sure we give the customer an adequate flow rate in order to meet the demand of the crop. Okay. And so, so the first thing we do is we look at the water sources, the groundwater, so we come up with an appropriate filtration for him. But the most important thing we're going to do, I believe, is to estimating the ET values. And where we find those, I mean, they tend to be very, like we know in the Central Valley that almonds, we're going to make sure that we provide 0.36 inches of water of application rate to the grower in order for him to be able to meet ET at full mature on the worst possible case scenario. And then from there, it's up to the grower to determine how much water to apply on a daily basis. So essentially, we're looking at, when we down lower on here, see if you can see this or not, but oh, I guess I can put my cursor here. This is gallons per minute of the crop. So think of it as the crop is actually transpiring off gallons per minute into the atmosphere, and that's ET, or evapotranspiration. So we need to replace it. So we're going to come up with a gallons per minute to replace that ET. We're going to add a little bit more because we're going to replace it not in 24 hours, but in 18 hours, and that's a rule of thumb. It allows us to have a little extra in case we need to. It also allows for the pump to break down, etc. And then we're going to add some gallons per minute. I put gallons per minute twice there, which is wrong, but anyway, gallons per minute to overcome non-uniformity. So we have a distribution uniformity of our system, and we're going to be able to add a little bit more water to overcome that. And the other thing is that drip systems tend to have less stress. So if you have less stress, you have more water that goes to the plant. So according to Cal Poly, how much more water? If you have a situation of no stress where you're irrigating a little bit every day or every other day, approximately 10 to 15% more water is going to go through that crop, go through that plant. And the good news is, as a general rule, the more water we put through a plant, the more crop we get. Okay? And then we also have, are we going to add the extra water? We have the extra water available to us when we size the system to account for flushing as well as delivering water to the crop. I'm a big fan of being able to flush and deliver all the water to the crop. We'll discuss that a little later. So we're going to target the optimum DU. So the optimum DU is, it can be crop dependent, it can be area dependent, those kinds of things. But as a general rule, we're looking at 0.9 or better. And that seems to be about the sweet spot for cost of the system versus highest possible DU, or distribution uniformity. This is a little graph that shows you how much under irrigation versus over irrigation given the DU that you have. So of course 100% one is flat, so you're putting on exactly the same amount of water in all parts of the field, which is unrealistic and not possible at this point because of the manufacturer's inability to produce a perfect emission device, as well as friction losses, elevation, et cetera, et cetera. So we're going to come up with some acceptable DU, and it tends to be about 0.9 to actually 0.95, depending on the system. And this is just to show you that as you increase the distribution uniformity, depending on the crop, you'll get higher yields. And I think on the very top it says tomatoes, but I know that bell peppers are very sensitive to over irrigation and under irrigation. So as a general rule, I know a lot of bell pepper growers will use 5/8 tape because they're concerned about drain down, as well as non-uniformity that comes with drain down, shorter runs, et cetera, et cetera. And then tomatoes are very sensitive to over irrigation, so higher DU is more preferable. Okay. Now this is an obvious non-uniformity where a drip system would really come in handy, right? I mean, you wouldn't have this on the ends of the fields. Now, one thing to consider is that if you have a field like this that has poor drainage on the end, that just by putting a drip system in it on the very next year, you may still have issues with that area of the field because of pathogens, et cetera, that develop over time. But anyway, this would be certainly, there are lots of fields out there that could really benefit from drip systems. Okay, how does DU affect your crop? Well, the higher DU you have, the less water it takes that you have to pump to overcome that non-uniformity, the less chemicals and fertilizers that you have to put in order to overcome that non-uniformity, and energy savings. And I think that the best thing that we can do as designers is to give you a robust system, easy to operate, with a high distribution uniformity, with a chemical injection strategy, and that's very energy efficient. And energy efficiency, as you'll see in a few slides coming up, it's really a consideration that we probably don't consider enough. Of course, when we specify an emission device, we do it in order to create a wetted area around the plant. As a rule of thumb, we're looking at about 60% wetted area of a plant. Now, having said that, that means that we have an area for the plant has some reservoir water so under times of like high water use, you have some reservoir available to you, broken pump, etc. And also just the structure of the plant. Like for instance, when a windstorm comes, if you have a very small wetted area, the plant's going to tend to occupy the root system is going to occupy that wetted area in areas where we don't have any supplemental water, like rain, etc., which is California and the West. Now, this is the picture I was talking about. The picture, the trees on the right are the same age as the trees on the left. And even though there are sprinklers there, you can see in the picture, those sprinklers aren't being used. There's 2 emitters per tree on the left, and on the right, irrigated with sprinklers. So the wetted area on the right is significantly more. It truly respects that 60% or 60% of the wetted area rule. And the emission devices on the left are what they call deep root irrigation. Has anybody heard of that? Anyway, the idea is that you put 2 point source emitters on a line, and then put it on this device that goes in the ground. And the idea is that it saves a lot of water. Well, I can also tell you that it saves a lot of yield, harvesting costs, because you can tell that you're not going to harvest very much on the left as you are on the right. So anyway,
that's pretty good, Perry. That's you may want to save money, but that might be one area that you don't want to save money on, right?
That's the one place you don't want. I mean, I get it. You want to save some money on water. Well, by just turning it off, you're not really saving water. I would argue they're wasting a lot of water on the left because you're not getting as much crop for the unit of water that you're applying. So even though it's less. Okay. So now we're going to go to the pumping station, and here we're going to appropriately size our filters. We're going to appropriately choose our filters. What kind of filters do we want? So we're going to probably confine our discussion to sand media filters because they tend to be very popular here in California on the West Coast. But there are other choices that certainly can be made. Pump protection, always make sure that we have pump protection. And if we're gonna have automation involved, which we have much more of it now, one very popular way to protect a pump is with a booster pump is with a pressure switch. But remember, it requires someone to be on site when you turn it on. So if you're doing an automation, if you want to turn on the pump remotely, you have to come up with a different plan for pump protection. Okay. Okay, so here we're at the pump station, and now we're looking at all the pressures that were, all the losses that we categorized. We've separated them out here, so we understand how much flow we need at what pressure. Okay, so that's just a very simple idea here. Now, one thing now, this is for dosing, or this is for the irrigation, this is for irrigation. Now, what happens when we flush? We're gonna need some more water and we're gonna need some more pressure, aren't we? So actually we could put this, we could present this differently if we wanted to, and say we're just during the flushing event, we're gonna require more pressure and more flow. Now, without a variable frequency drive pump, it's probably not practical to do it that way. So now let's just talk a little bit about energy. Now take a look at this equation. Notice that on the top you see P and Q, which is pressure and flow. So what this tells me is that the kilowatt hours requirement is directly proportional to pressure and flow. So can I lower my flow? Not really, because I need to apply the water that the crop requires. The only way I can lower my flow rate is with better distribution uniformity, because now it's going to take less water to overcome non-uniformity. But how about the pressure part of it? If I can lower my pressure by 10%, I can save 10% of my energy. It's pretty much that simple.
So Perry, we had a question about distribution uniformity, and it's this.
Yep.
Do you have a favorite method to determine DU in a system that you've used for a while that's been effective?
Essentially, what we're targeting is we're gonna have a system that's gonna have a variation in flow rate that will give us a distribution uniformity of 0.9 or higher. And that's sort of the minimum required that's reasonably cost effective to provide to the grower. And generally, most crops are going to do well under those situations. Now, if we have something like tomatoes or bell peppers, we're going to really shoot for that or higher. So maybe 92%, or excuse me, 0.92 or 0.94. You understand what I mean?
Yeah, yeah.
Okay. So now we're talking about energy. So let's just assume that the cost of energy is 20 cents a kilowatt hour. I don't know what it is in your area, and you can go up or down. And we have a drip line that has a minimum pressure requirement of 10 psi. Well, the cost to pump an acre foot at 10 psi is $7.38, given we have a 20 cents per kilowatt hour. Now, with a micro sprinkler, we might have a minimum pressure requirement of 30 psi. Well, notice what the cost to pump an acre foot is at 30 psi. And of course, that reflects all the way back through the system. So you can expect this kind of ratio difference when you look at one emission device versus the other. Okay. So we're not going to talk about too much about variable frequency drive pumps, but if someone were to ask me how much could I save with a variable frequency drive versus the standard board, what would I tell them? My standard answer is somewhere between 10 and 15%. And why is that? The reason is because if we look at an irrigation design and the pressure requirements, and I'm going to order a pump with a standard board that's going to run at 60 hertz, I'm going to have to order it with 10 to 15% more pressure and flow than I need, just to make sure that I have it. And with a variable frequency drive, I can still order the pump with the additional flow in it and pressure, but we can turn it down and take advantage of those savings. So that's the bottom line for me.
Yeah.
Okay. So filter stations. So as a general rule, I like to provide for the flushing and the flow rate to the field. So during the flushing event, how much water does it take? Well, it takes approximately 200 gallons a minute to flush a 48-inch tank, or 195 gallons a minute. And so what I like to do is calculate the additional pressure and flow that it's going to take, so that I can flush and I can also deliver the water to the field, so that we're never in a place where the uniformity goes down in the field because of low pressure, or the effectiveness of the irrigation is significantly less. So, and it also gives you a perfect flush every time, because you have the same pressure, because the pump seeks the pressure that you need in order to make it work. Okay. Some of the other things that we do is we want to make sure that we have the correct filter size. Like, how many filters should we have? Depends on the water quality and how many gallons a minute are we going to put through each filter, given the water quality issues. And what I just described as the flushing strategy, are we going to use a pressure sustaining valve, or are we going to provide with a VFD, which means it'll provide the additional flow and pressure when we need it only? That's my strong recommendation, has been with a variable frequency drive. And most people are extremely happy with them when they get them and they understand how they work and how it works for them. Okay, strategy for pipe sizing, manifolds. It's completely, what drives the design is downstream of the pressure regulating point is distribution uniformity or emission uniformity. Okay, so we have an emission uniformity of a lateral, and then we have a pressure variation allowed to us within the submain in order to attain that. Now, if we're using pressure compensating product, then the pressure regulating point is actually the emitter. So that's the critical path, is to the most distal point of that emitter and back to the pump. And so we're using economic pipe sizing in order to size. So that's our strategy. You'll also notice that it says right here, keep velocities less than 5 feet per second. Well, why 5 feet per second? The reason is something called velocity head. And I won't get into the weeds too much here, but velocity head and the impact on the irrigation system is trivial below 5 feet per second. So we don't have to worry about it so much. Above 5 feet per second becomes an issue. Okay.
So Perry, on these manifolds and your filter systems, how do you feel about injecting fertilizer downstream of the filter?
You know, I've never won that argument so far. You know, I mean, farmers love to inject downstream of the filters because they're afraid to flush the chemical out, or they're afraid that the filter's somehow going to keep some of the fertilizer back. You know, and I'd say count yourself lucky if the fertilizers plug up the filter. You know, by applying it downstream of the filter, it means that, I mean, my general thing that I say to people is, if it can't go through your filter, it can't go through your system. I mean, that's what the filter's there for, right?
Right.
And we're smart enough to figure out how to shut the fertilizer injector off previous to it's going to flush. You know, previous to the flushing event. So we should be able to turn off the fertilizer, so we're not flushing fertilizers back into our to wherever the flush water goes. if we do that. But now, have that being said, most guys like the simplicity of just injecting downstream of the filters. I get it. I totally get it. And I would say that there's less disasters out there than there used to be, you know. But if it were me, I always suggest injecting upstream of the filters, depending on what the product is. Some acids go downstream because if you're injecting a strong acid, they can't go through the filters. If you're injecting an acid as a water treatment, well, then it can go upstream of the filters. And there are a few products that are not meant to go through a filter. That being said, I still strongly advocate putting the injection upstream of filters. Excuse me.
So another one of those, it's not a deal breaker. You're going to listen to your customer, but
yeah, but
if,
you know,
if it was up to you, it'd be upstream of the filter.
Well, you know, I learned that you can lead a horse to water, but you can't make them inject their fertilizer upstream of the filter always. And there are times when I'll agree with them, it's not perfectly appropriate. But anyway, be cautioned, you know, that if you're doing that, you could potentially have a disaster. Okay. So this is just showing that there are different materials that we can use. Oval hose, lay flat. Here we go. Here's Aqua Flat. It's another product that Jane sells. And valves and pressure regulation. Well, certainly do it when it's appropriate. For instance, if you're using pressure, don't over pressure regulate your system. I mean, because there's always a loss. So if you're using pressure compensating emitters, then don't put pressure regulation in front of it unless you need to somehow limit the amount of pressure that goes to it. There's elevation. There are valid reasons to put pressure regulation in front of that, but don't do it unless you have to. Okay, because there's a loss in pressure and efficiency essentially every time you do something like that. So use pressure regulating valves when it's appropriate. Okay.
Okay.
And there's different, and of course there's different strategies, whether you're using inline pressure regulators, and there's also a loss with those, and there's a cost of uniformity with those as well. And then the last one that was put in here was using spaghetti tube. That's generally done in places of elevation with drip tape. It's probably not done that much in California. Probably done a little bit, but not much.
So we had a question about energy costs again. So back a couple slides, right?
Sure.
And since energy costs increase with micro sprinklers, what strategy do you use to offer micro sprinklers versus emitters? I mean, there's lots of people using micro sprinklers, right?
Yes, there are. And what this boils down to is the benefits of micro sprinklers, or using those micro sprinklers, worth it to you. There's nothing I can do to make it cheaper. You see what I mean? It's going to cost additional pressure within the system in order to make a micro sprinkler work versus a drip line.
Right.
There's just no way to get around it. So it's up to the grower to decide whether or not that cost is worth it to him. I mean, there are frost benefits. I mean, frost control benefits. There's a lot of wetted areas. The wetted area is easy to get with a micro sprinkler. Maybe you can't get it with a drip line. So there are very good reasons to use micro sprinklers versus drip line, but just you have to understand what those costs are.
Right.
And you have to justify those costs to you have to say, oh yeah, it's worth it to me to do that.
Yeah. Okay, that helps a lot. Thank you.
Let's see, let's go back to our air vents. Air vents are probably one of the things that are most misunderstood in proper installation, sizing, and location of air vents is really important. As a general rule, designers are using a rule of thumb in order to put these air vents in, and as a general rule, it works beautifully. I mean, those rule of thumbs work just fine, and some of them are listed here. I think of air vents as kind of like safety belts. You know, when you get in a car, if you don't get in an accident, you don't really use that safety belt, but you put it on. And so essentially, you could go out to an irrigation system and take off all the air vents, and it might work. You know, but there are going to be times when it's not going to work, or you're going to blow up a line or do something like that. So that's why they're there. So if you look at your irrigation system, it's got no air vents on it, it's probably you potentially have a problem. Okay, and here's one of the problems is back siphoning, and we won't talk too much about this or the cause of it, whatever. But generally, it's elevation and not a properly designed system. That's why you have to have air vents on your submains that will prevent that from happening. When at shutdown, you can have back siphoning into your emission devices, drip tape or hard hose and emitter. So by the way, drip tape is a little more forgiving to back siphoning than hard hose and emitter, because the hard hose and emitter has a volume that stays there where the drip tape collapses. So it's a little bit more forgiving. Drip tape is, by the way. Okay, there's air vents. So proper size and placement, and also function. Some air vents are able to, continuously acting air vents are able to take air out of a system that's under pressure, and a large acting provide vacuum relief and on initial startup a lot of air removal. And one of the ones shown here does both. Okay. So again, the fertigation, I mean, have a strategy for fertigation. As a general rule, I always advocate putting the fertilizer injector upstream of the filters and turning it off when we flush. But you should have ports on both sides because there are going to be some materials that can't go through the filters for whatever reason, and also acid injection. And with that, I don't know where we are in time, but we can entertain questions.
Yeah, that was great, Perry. Thank you very much. A lot of valuable information there, and it'll be easy for me to keep in my mind as the 10 steps. So, yeah, we've got we got a few minutes here for some questions. And I know one thing, that I love about learning is sometimes I learn that I really need to get a professional to help me do things because there's a lot more to it than I originally understood. So, if somebody is going to hire a designer, what type of pricing is out there for them? What pricing should they be looking for? What's fair and reasonable? What do you think about that? I'm sure there's
the culture is different parts of the country. For instance, if you go to Napa was always a place where they had independent designers. So the independent designers would design the system, give you a design, and then you would go and then buy your system from someone else. And I think that's a good approach, because then when you get say two companies trying to get your business, maybe one design might be cheaper, but you start looking at the energy use, the robustness, did they skimp on the filters, et cetera, et cetera. The cheapest design obviously isn't always the best design. So, and as far as independent designers out there, I think it ranges anywhere from $10 to $15 an acre for the design. And, that's just, but as a general rule, a lot of the companies are doing the designs. So if you're getting a price between two companies, you're getting probably two different designs.
Yeah. Yeah, well, I'll tell you, if I'm putting that investment in the field, 10 to 15 bucks an acre is a pretty sound insurance policy, if you ask me.
Mm-hmm. And I would say look at the number of filters, look at the energy use, and I think that more designers should be putting like how much it costs to pump an acre foot of water right on the design. And
Yeah.
I will admit that I haven't always done that as well. So I'm as guilty as anybody.
Right.
But I do like to point that out. When I say do a system for someone, I try to provide them with you know, the horsepower requirement to flush and provide to the water in the field. That's what I like to, that's the way I like to do it. I've come up with I've won designs and lost, I mean, I've won jobs and lost jobs with that. So
So what software do you use to design, and why do you use that?
I'm using Irrigation. I'm also using length of run calculators from different manufacturers. One is on the, again, one is right on the Jane website. You can go on there, and then Excel. So I use a number of things to design myself. A lot of the designers, probably the culture right now is to use Irrigation, which does what you saw earlier was done with Irrigation. It does a nice job with elevations. There are some limitations to it, but I believe it's probably the best irrigation program out there.
Right. Okay. Great. Well, let's talk backflushing for a little bit.
Okay.
How long do you recommend to backflush a filter?
We generally set it up for about 2 minutes per backflush, and you're looking at approximately 195 gallons a minute per tank to flush for 2 minutes. So if you've got, you know, you can figure out how much water you got to get rid of. And so the other thing that I meant to discuss was, we always ask the question, what are we going to do with the backflush water? You know?
Yeah. And what's that answer?
It ranges from, oh, we've got a pond, we're going to dig a pond, we're going to put it back into the canal, etc. To, I don't know, you know? That's
yeah, it's just going to go out.
Yeah.
On the ground.
Yeah.
Yeah.
So we have a mess.
Yeah. And so what's the pressure differential requirement for backflushing?
Like all irrigation answers, it depends.
Yeah.
But there's a simple way to calculate it. So essentially, if you've got more than 2 filters, by the way, that's probably the thing that I should have mentioned in this, is that we always recommend a minimum of 3 filters, even if you downsize the filters in order to get 3 filters, because of the flushing requirement. Essentially, we're asking, if you have 2 filters and we're trying to provide the water to the field and flush at the same time, we're asking 1 filter to provide all the water that the other filter is providing during flushing, plus an additional 195 gallons a minute for the flush water. It's impossible, because you'd need a huge amount of pressure to do that. So the way that I like to do it is to calculate how much additional pressure and flow I'm going to need, which is the additional flow is 200 gallons a minute. And the additional pressure is, as a general rule, it comes into about 8 to 12 PSI of additional head pressure during the flushing event. And if you don't get that pressure available, if you don't have that pressure, then you won't get an adequate flush. And so it's like a vicious circle. You don't clean the filter every time you flush, and so you flush more often.
Right.
So by being able to provide the additional pressure and flow you need during a flushing event, then the field never suffers for lack of water, proper water with the proper DU, and you get a perfect flush every time. So you're not flushing out the sand or media, and you're not cleaning the filter completely during with low pressure situations. So that's why I strongly have recommended variable frequency drives to accomplish that.
Yeah. Yeah, smart. Yeah, very interesting too. So we've got another question here, and the question is, what is the critical path in a drip system?
Okay, well, that tells me I didn't explain it very well. So the critical path is the most distal point that we need to have a certain pressure. Now when I say distal point, that means distal point hydraulically. So it could be, if it was on a perfectly flat field, it'd be the farthest point from the filter, from the pump. And if it's has elevation of involved in it, then it's the place that requires the most pressure to get the water to. Okay.
Right. Yeah. Okay. And yeah. So, and I don't know that it necessarily means you didn't explain it well. Sometimes we don't hear it all that well. So,
well.
So, and then we've got to have, this is probably one of my favorite questions of all the lunch and learn so far. So that's a heads up on this. And somebody wants to know if insects really bite on the tape and the emitter line. Is that really an issue?
Absolutely. And if you go to the Cal Poly website, ITRC, they have a nice document that shows pictures of all the different things and what it looks like. But essentially, if you look at drip tape, the way that we determine what happened to the drip tape is you look at it and you ask yourself, was that drip tape moving when that hole got there? If it was moving, there'd be drag lines, okay? And when the drip tape is manufactured, it's manufactured in one direction, and when it's paid out in the field, it gets paid out in the opposite direction. So we can have a good idea of how to determine where that drip tape was compromised by drag lines and what direction they are, or no drag lines. It was stationary when it was when the hole was gotten there. And also you'll look at, say, like ants, for instance, they do like a thrashing. And so you'll look at, it'll look like a little sort of a nest of where they chew through it.
Yeah, so it's ant management now, and not.
Well, there's all kinds of different wireworms, et cetera, and there's different things that you can do to I guess products that you can put in the tape to protect it, et cetera.
Yeah. So listen, Perry, you've done a great job today. Thank you so much. I want to give Kevin Stewart, our Director of Sales at Jane, I know he wanted to pass on a few messages before we signed off today. So Kevin, good afternoon. How are you?
I'm good. Thanks, Richard. Hey, Perry, thank you so much. Great
welcome.
job. We appreciate your time and effort in putting something like that together. We're always looking for great people to share their insight. I just wanted to take just a quick opportunity, thank everyone that attended this webinar, and as a way to say thank you for anyone that registered for this webinar. So if you gave us your name, your email address, phone number, we're offering an extra 5% discount on any new orders for Turbo Tape, which is one of our drip tape products. We felt like that was appropriate, given that we're talking about drip irrigation design. And so if you've got a vegetable crop or row crop where you're looking to use anything from maybe a 5 mil to a 10 mil, either in 5/8 or 7/8, we've got a special. We're going to run it through the end of this week, and just go ahead and contact me, and we'll kind of work out the details. So we'll put a maximum of 528 reels, which is a truckload. And so, yeah, if you're interested, please get with me. My email is included on here. My phone number is included as well. So if you want to reach out, we can kind of work out the details. If you're a grower or an end user, we'll work that out with your dealer and just work out the details. So again, thank you so much for joining. Richard, I'll turn it back to you.
Yeah, and thank you, Kevin. That was a really generous offer. I know a lot of people will be taking you up on that, and contact Kevin to take advantage of that. That's a great deal. And Perry, again, thank you so much. You did a great job. A lot of anticipation for this, and you didn't disappoint at all. So thank you. You were great. Want to remind everybody on Friday, we're going to have a landscape panel. We'll have someone from manufacturing, a contractor, as well as a distributor on to answer questions about how they're operating business during this COVID-19 situation. Should be really illuminating, I think, to hear the changes people are making in order to not just stay in business, but actually thrive. And so we've got some good stories on that. So hopefully you'll join us on Friday. Again, Perry, thank you. And thanks to everybody else for joining us today. Bye now.
My pleasure.
Thank you.